And so we're going to have our last two talks before lunch. Our next speaker is Professor Pablo Jarillo-Herrero from MIT. He's the Cecil and Ida Green Professor of Physics at the Massachusetts Institute of Technologies. And he's become, I guess, the wonderkind of moire in the sense that exploring this path to a whole new wide array of both materials design and condensed matter interaction design in multi-layer materials. And so I'll get out of his way and let him give this talk to you. Thank you.
Is this working? Yep. Very good. Thank you very much, Bill. It's really a pleasure to be here with all of you. Okay, I've been looking forward to this event since Bill told me, last year that he was organizing, and it's really fantastic to see it happening. So I want to tell you a little bit about this, this field of, combining materials and rotating them, and which I popularly, some people refer to twistronics, and hence, magic angle graphene and the twist and shout, has become the twist and shout of quantum materials, But before I go into more to the materials and so on, I want to first to start from a more general point of view about talking about the emergent behavior of quantum matter. Okay, so it turns out in physics, we have two types. One could say that we have two types of physics: the physics of a single object, for example, an electron spin, and this is something that the behavior of a single particle is quite simple. And by quite simple, I mean we understand it. Okay, we can describe it theoretically to a pretty high degree of precision. However, when we have many particles, many objects, for example, many electrons, okay, interacting with each other, that behavior is difficult. And by that, I mean we do not understand it theoretically. We don't know how to describe it. Okay? We don't have the appropriate mathematics, or we don't have the appropriate, the sufficient amount of computational power to theoretically understand these type of problems. These are many-body physics problems. However, the majority of the most fascinating states of matter that we have in the universe are due to these type of effects, where many particles are interacting very strongly with each other. Right? So this is something that happens, for example, in the quark gluon plasma, which is a state of matter that happens a few hundred nanoseconds, microseconds after the Big Bang, and that we can recreate nowadays in high-energy physics accelerators, okay, such as Brookhaven National Lab, when you smash heavy ions with each other. These many-body phases of matter happen also, for example, in neutron stars, which result, is the object that remains after a supernova explosion. Yeah? In these objects, neutron stars, you have very strongly interacting neutrons, and there are different layers and different phases of quantum matter depending on various parameters that are related to the interaction and the pressure and all kinds of things in these neutron stars. And a little bit closer to my field, to condensed matter physics, when you subject a system of electrons into dimensions to a strong magnetic field, you can enter this regime called, or this quantum phase called the fractional quantum Hall regime, where electrons acquire very unusual properties. For example, they seem like they have a fraction of a charge instead of an integer charge. They also, their wave functions acquire very interesting mathematical properties related to something known as topology. And this is something that is, again, due to the many-body behavior of interacting particles that we have a hard time describing theoretically. If you go into now the field of strongly correlated quantum materials, the most famous of which is probably are the high-temperature cuprate superconductors. Okay, this is the image of a superconductor, floating there. And in a phase diagram of temperature versus doping versus charge density in these high-temperature cuprate superconductors, we have a variety of phases, strange metal, pseudo-gap, the superconductivity itself, etc., that we really have very little understanding of, despite many decades, almost 40 years now of research into these materials. Now, let me give you a little bit of a sense for why this happens. So, this, high-temperature cuprate superconductors, all of the action takes place in a single metallic, in a single plane called the copper-oxygen plane. Okay, and when you grow a material without chemical doping, you have 1 electron per copper atom. That's 1 electron per unit cell. Yeah. Turns out you can put up to 2 electrons per copper atom in the system. So these electrons actually should be able to jump from copper atom to copper atom and conduct very well. However, the strong interaction, the strong repulsion between these 2 electrons, okay, prevents them from transporting charge, and you have something known as a correlated Mott insulator. Okay? Now, something very interesting happens if you remove a few of these electrons. You dope with holes, or you remove a few of these electrons. Okay? Turns out now, because you have some empty spots there, the electrons are no longer repelled by the existing electron there because it's not there. And now the electrons can jump from occupied to empty side. And they do this in a correlated fashion, that almost magically gives rise to high temperature superconductivity. Yeah? The basic physics that governs this behavior is believed to be that of something known as the Hubbard model, which is a theoretical model that contains just 2 ingredients. The repulsion energy U to have 2 electrons occupy the same spot. That's that repulsion that I mentioned earlier. And then the energy of hopping between occupied and unoccupied states. Yeah? And I say we believe that this model contains essential ingredients because we actually cannot calculate, theoretically solve this model, even for the simplest assumptions, for more than a few electrons. Okay? We can certainly not do it for 10 to the 23 electrons. Okay? So we do not know yet, or there's no agreement between theorists, among theorists, how to go from this type of model to this type of phase diagram. Okay? There are many proposals, but theorists don't really agree. People have to make different types of approximations, and some people don't like those approximations, etc. And as a result, there's no consensus on how to go from this to something like this. Now, this difficulty to analyze this problem of strongly interacting particles theoretically has led to alternative approaches to try to investigate strongly correlated matter. Yeah? And one of these approaches, which is most successful, and I'm sure you will hear some about this today or tomorrow, are the field of ultra-cold atoms in optical lattices. Yeah? So what you can do there is you take a laser, you take 4 lasers, make 2 lasers, you make a standing wave here, 2 lasers, you make another standing wave. So you have a standing wave, like this thing where you can load atoms, like the same way you put X, in an egg, thing. And you can tune the interactions between the atoms that you load in your periodic potential such that, for example, already 20 plus years ago, they were able to realize a transition between a Mott insulator and a superfluid, okay? Just by tuning the interaction strengths between these atoms. Now, this was done for atoms that had an integer spin. So this was a realization of the Bose-Hubbard model. Okay? A few years later, people did this for atoms with half integer spin. Okay? That is closer to what electrons look like. Okay? And this was a realization of the Fermi-Hubbard model. And some of the things that people are doing lately in the community is that they have been able to realize anti-ferromagnetism in this Fermi-Hubbard model. So, this is a quantum gas microscope where you can load atoms and you can see, blue and white means spin up and spin down. And you can see that this short-range anti-ferromagnetism, that has been realized in these structures. So as a result, the cold atoms community is beginning to explore this corner of the phase diagram, Mott, anti-ferromagnetism. They would like to explore the entire phase diagram, especially this region of D-wave superconductivity or superfluidity in atoms, okay? Which is very interesting. However, the cold atoms community, even though their temperatures are of the order of a nanokelvin or a few hundred picokelvins, that temperature is still too high by 1 or 2 orders of magnitude to realize some of these interesting phases that they've been looking for a long time. Yeah? So it is very hard to cool down the atoms further. Not impossible. It's not forbidden by any law of physics. It's just very challenging technically. Yeah? And as a result, they haven't been able to realize as many quantum phases of matter as they would like. And what I want to tell you about today is the following. So we have these 2 quantum materials platforms that have been traditionally investigated. Quantum materials where the typical scale is atomic scale, an angstrom, a few angstroms. Okay? Here we have hundreds of thousands of materials. Each time you want to explore physics of one material, you have to go to a different material. We have relatively little tunability of the parameters of the materials. We have many materials. We have to grow each one chemically and then explore them. On the other end, we have, for the past 20 years or so, ultra-cold atoms in optical lattices. Here, the length scale, the characteristic length scale is 1 micron, the wavelength of light. Okay? Here, you have exquisite control over all the parameters of your system. Because they can tune with lasers, they can control absolutely everything. However, they have not been able to realize many phases of matter because of these difficulties, among other things, with the temperature of their system. And what I want to tell you about today is about this new platform that has emerged over the past 6 years or so. It's called the Moiré quantum matter, where the typical length scale now is 10 nanometers. So it's conveniently about 2 orders of magnitude from either of these other 2 length scales. Okay? Associated with these length scales are energy scales. For example, in quantum materials, typical energy scales for parameters are 100 to 1,000 Kelvin. In cold atoms, 0.1 to 1 nanokelvin. In Moiré quantum matter, 1 to 100 Kelvin, which is a convenient energy scale or temperature to investigate in a solid-state physics laboratory. And what I'm going to briefly tell you about is the fact that in this platform, it's also very nicely complementary, in the sense that we do have quite a bit more control than with traditional quantum materials. Not as much as with the cold atoms, but we have been able to realize many, many phases of quantum matter. Okay, so I'll briefly tell you. So initially, the thing that enabled this Moiré quantum matter platform is the fact that when you have 2D materials, you can do something that was impossible to do in the history of material science before. You can control the relative angle, the relative rotation angle between crystalline planes completely at will. So for example, I can take a sheet of graphene, which is a honeycomb of carbon atoms. I can put another sheet on top with any angle of rotation between the 2 crystalline planes. Usually, thermodynamics, physics, chemistry tells you what the angle between planes should be in a structure. But now with 2D materials, I can put them on top of each other with any angle that I want. Yeah? I choose that angle. And the amazing thing is that the electronic, optical, mechanical properties of the combined heterostructure can differ dramatically from the constituent layers. Yeah? So using this trick, which sometimes is known as twistronics, okay, people, okay, the community, we have been able to realize pretty much all of the phases of quantum matter that we know and discover quite a few new ones which didn't exist before. Yeah? So using this trick, it's called Moiré quantum matter because the Moiré pattern that forms when you superimpose 2 periodic structures and rotate them one with respect to the other. You can also do the same trick without rotation if those 2 lattices are not identical. You also form a Moiré pattern. Yeah? And using this trick of looking at Moiré quantum matter, we have been able to realize correlated insulators, new types of superconductors, many topological phases, magnetism, quasi-crystals, new types of ferroelectrics, strange metals, generalized Wigner crystals, excitonic insulators, pneumatic systems, and the list continues. Pretty much all of the phases of quantum matter that we know. Yeah? So, okay, with that introduction, this is what I'm going to tell you about today. I'm going to take a step back, a little bit more to the basics of material science, tell you a little bit about how, what determines the properties of materials, or what did we think determine the properties of materials. Then I'm going to tell you about graphene and magic angle graphene. Then I'll say a few words about the rise of Moiré quantum matter, how this field now has emerged and in which directions this is going. And then a little bit about the outlook. I hope to have a few minutes left for an outlook for how this is impacting beyond electronics, beyond condensed matter physics. Yeah? So let's see if we can get through all of this. All right. Now, what would you say determine the properties of matter, okay, of materials? A good first guess is the chemical composition. Yeah? For example, gold is a good metal. Yeah? Aluminum is a good metal and a superconductor. Okay? Iron, is a metal and a magnet. Okay? You know that if you want a magnet, typically you need iron or nickel or cobalt, etc. And silicon is a semiconductor. Okay? So you may think like, oh yeah, if I want a given property, I just have to go to the right place in the periodic table. Yeah? That's a good first guess. But it's certainly not all that, because we know, for example, that carbon, okay, doesn't give you always the same behavior. Yeah? For example, you have graphite, okay, which is an electrical conductor. Okay? Pencils are made of graphite. If you write with a piece of graphite with a pencil and you connect 2 electrodes, you can measure a current between those in that trace. But we also have diamond, as you have heard about earlier today, which is actually an electrical insulator. But both are made just of carbon. So what is the difference here? The difference is the structure, okay? They behave very differently because the carbon atoms in graphite and diamond are arranged differently. They have different crystalline structures, which you can see here. Graphite is a layered material. Each of these layers is graphene. It's a honeycomb of carbon atoms. Diamond has this three-dimensional structure. It's not a layered material. Okay, they have different crystalline structures, and that's why they have different behavior. Okay, so both crystalline structure and chemical composition are important aspects that determine the properties of materials. And usually for a given material, okay, nature, meaning the laws of thermodynamics, usually determine the most favorable crystalline structure. And there's not too much that you can do about it. Okay? Usually the crystal structure cannot be changed for a given material. Okay? Or you have little flexibility usually. But that was until 2D materials appeared on the market. With 2D materials, yeah, you can do much more, as I just briefly showed earlier, and I'm going to tell you a bit more about now. Huh? Okay, so graphene. So graphene is a honeycomb of carbon atoms. All of these atoms are carbon. So from the chemical point of view, they are all identical. However, from the crystallographic point of view, we have two types of carbon atoms. We call them the A and B carbon atom, or the red and green ball here. Okay? And that is because in order to tile a honeycomb, okay, you need not only two vectors, but also two atoms in addition to two vectors. Okay? You have what is known as a two-atom basis. Now, you can calculate the electronic properties, the electronic structure, yeah, of electrons in graphene in a simple quantum mechanical model. And that tells you what the energy versus momentum in the x direction and the y direction, so 2D, yeah, looks like. This is a very unusual electronic structure for most materials. This energy is the kinetic energy. The kinetic energy is quadratic, right? Parabolic, right? P squared over 2m, you know, the usual stuff. Okay? However, for electrons in graphene, near the Fermi energy, you know, near zero energy, you have this linear energy momentum dispersion. That looks more like the light, you know, where the speed of light is always constant regardless of their energy, right? Those famous Einstein cones, okay? But this is for electrons in graphene. Okay? In fact, if you look, you know, in detail at what is the formula that describes the behavior of these electrons, the equation that describes the behavior of these electrons in graphene, is this one, is nothing else but the Dirac equation in 2 dimensions for massless particles. Okay? This is the only formula I'm going to use in the talk, so don't worry. Okay? In the usual Dirac equation, this thing is called a spinor, which tells you whether the electron spin is up or down. Here is a pseudo spinor, which tells you whether the electron wave function is on the A type of atom or on the B type of atom. Yeah? Now, the only other thing I want you to remember about this thing is that we have two of these, you know, double cones that are called the K and the K prime valleys. So we say that electrons in graphene can have spin up or spin down and be in the valley K or in the valley K prime. So 4 degrees of freedom. Just remember number 4. It will appear later. All right? Very good. So this is a single sheet of graphene. If you put one graphene sheet on top of another and you rotate the angle between the two sheets, you can see that a moire pattern forms where the moire wavelength, which is the distance between the soccer balls that you see here on the screen, yeah, is roughly inversely proportional to the twist angle, at least for small angles. Yeah? Now, this is in real space. Let's think about what happens in momentum space and therefore what happens to the electronic properties when you do this. Yeah? So I have here my single sheet of graphene. This is the graphene electronic structure. This is the Dirac cone. If my Fermi energy, the energy of my electrons is somewhere above here, because this is a cone, I have a Fermi surface, you know, that looks like this. These are the K and the K prime points in the Brillouin zone. Okay? Let's put another graphene sheet on top. If it is exactly aligned to the previous one, in reciprocal space, in momentum space, those electronic structures are also aligned. Okay? If I now rotate, you know, one layer with respect to the other, these reciprocal spaces of the two layers also rotate and by the same angle. Yeah? So there is a separation in momentum space between these Dirac points, which is proportional to sine of half the theta, the twist angle. Yeah? So twisting leads to the layered Dirac cones, the electronic structures of the two systems decoupling, separating in momentum space. Yeah? Let's assume that we start from a small rotation angle, okay? So that the separation in momentum space is proportional to the angle, okay? And then let's see what happens. Here we have separation in momentum space proportional to the angle. This is the Dirac cone of layer 1 of graphene. These are the electrons in Dirac cone layer 2 of graphene. This is the situation that would be realized if the two graphene sheets, the electrons in one graphene sheet did not know that the other graphene sheet is there. However, because when I put graphene on top of graphene, these are just 3 angstroms apart, separated, the electrons are very much aware that the other graphene sheet is there. In particular, they can tunnel back and forth between the two graphene sheets, quantum mechanical tunneling, okay? So this interlayer tunneling leads to a repulsion there, band repulsion at that crossing point. This is the exact same thing as bonding anti-bonding states in a hydrogen molecule, but this is bonding anti-bonding bands in a giant graphene molecule, okay? So that thing, as you can see, pushes one of these bands, one of these, that crossing point opens a gap and pushes it to lower energy. If I now continue decreasing the twist angle, when I decrease the twist angle, my Dirac cones come closer and closer and closer together. Remember, at 0, they're on top of each other. So they come closer and closer and closer, and this thing gets pushed down, 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 until there is an angle for which, a flat band condition is realized. That energy, that band gets pushed down all the way to 0. Okay? That flat band condition is reached at an angle called the magic angle, and it happens to be 1.1 degrees for graphene on top of graphene. It depends on that interlayer tunneling. Yeah? This is something that there was some experimental work, and theoretical work by Bistis and McDonald, Suarez Moreira also. In these papers and earlier papers, the single particle physics behavior of all of this was more or less understood. Okay? What nobody knew is what would happen with the many-body particle aspects. Huh? So this was a cartoon. Let me show you an actual electronic structure calculation. This is energy versus momentum, okay, projected in one dimension. And you can see that these are flat bands. This is no longer these steep Dirac cones. It's something very flat. Okay? It's not completely flat, but it's much flatter by orders of magnitude with respect to the original graphene dispersion. So the electrons in this magic angle graphene here have very little kinetic energy, only a little bit compared to the original one. Yeah? Now, flat in momentum space, if you want to now go back to real space and see where those electrons are, okay? To go between momentum space and real space, you have to do a Fourier transform, okay? And the Fourier transform of an extended object is a highly peaked object. And that means that when you look at electrons, when they are in these flat bands, where do they like to be? Turns out they like to be in certain regions of your Moiré pattern, which we call of AA stacking, which means locally it looks like all of the carbon atoms are on top of each other in this twisted structure. If you move a little bit away, you go in these regions of ABB stacking because, because of the small twist angle, the registry shifts and changes. And in those regions, the electrons do not like to be. So what magic angle twisted Valeria graphene looks like, schematically, it's like this. You have these regions of AA stacking where the electrons like to be, separated by regions of AB and BA stacking where the electrons do not like to be. In a slightly more realistic schematic, magic angle graphene looks like this. You have these regions of AA stacking shaded in yellow and separated by about 13 nanometers where the electrons like to be, and then separated by these regions where the electrons do not like to be. This is sort of going to be an analog of that cold atom simulator, lattice, okay? Where we're going to put electrons there and play with them, okay? Now, this is an analog of a triangular Fermi-Hubbard lattice in cold atoms, but I put triangular in quotes because in reality, AB and BA are not identical. This is actually a honeycomb structure, not a triangular structure. And Fermi-Hubbard in quotes also because this lattice has very interesting topological properties in its electronic structure, which prevents a direct vanilla mapping to the usual cold atom lattices, okay? But you get a little bit the spirit of it. This is going to be like those cold atom lattices. We're going to play with it. Okay. Now, so we make our devices, and we have a structure where we have the magic angle twisted Valeria graphene. This is encapsulated between two sheets of, 2 flakes of hexagonal boron nitride, HBN, which is just a material that makes sure our magic angle graphene stays very pristine, okay? And its electronic properties can be measured very nicely. We contact them with source and drain contact. So if we apply a voltage, we can measure a current circulating through this thing. And then, very importantly, we have a nearby metallic plate. This metallic plate and the magic angle graphene form a parallel plate capacitor. So if I apply a gate voltage, then I can vary the charge density in the plates of my capacitor, in particular on the magic angle graphene. Okay? For those of you that have some engineering background, this is a field effect transistor geometry, okay? To vary the density of the two-dimensional metallic system, conductor. So before I show you actual data of what conduction through magic angle graphene looks like, let me remind you or show you, probably for some of you for the first time, what conduction through regular graphene looks like. Yeah? So if you measure the conductivity of graphene versus density of electrons, if your Fermi energy is deep into the valence band, you have lots of holes here, and those conduct very well, so you have high conductivity. If your Fermi energy is deep into the conduction band, you have lots of electrons, and therefore you also conduct very well. If your Fermi energy is near the charge neutrality point, you don't have much charge carriers, and therefore it conducts poorly. So the conductivity of graphene versus density looks like this V shape. Yeah? And this has been measured by thousands and thousands of groups around the world. Yeah? Let me show you now what happens with magic angle graphene. So this is the actual conductance, okay, of a magic angle twisted bilayer graphene device as a function of charge density. You can see that near zero, it has this V shape. It kind of remembers that it comes from graphene, okay? But then you have this, down and up and down and up and down and up and down. It gets a little bit crazy, okay? So let's try to understand what's going on here. This is the electronic structure of magic angle twisted bilayer graphene. I showed it to you earlier. It turns out in these flat bands, okay, if you start from zero, to get to the top here of the band, you have to add 4 electrons per more unit cell to the system. Remember I told you to remember 4? Yeah? If you want to empty this band from zero, you have to remove 4 electrons per more unit cell. So you have in total actually 8 electrons per more unit cell that can fit in these flat bands. Yeah? So with this charge density, which by the way I control electrically, just with the voltage, okay? What I can do is the following. I can go from zero, remove 4 electrons or add 4 holes per more unit cell, and my chemical potential will go here. This is in the middle of a band gap. There are no available states for the electrons to conduct electricity, and therefore this is an insulator, zero conductance. This is a single particle insulator. We understand why the electrons do not conduct. They don't have any available states to conduct. This is filled, this is filled, this is empty, they're in between, there's nothing to conduct, okay? The same thing happens if we put 4 electrons per more unit cell. Our chemical potential gets up there, no available states for the electrons to conduct, therefore it's an insulator. That's easy to understand, okay? The interesting thing happens when you put 2 holes per more unit cell. At 2 holes per more unit cell, your chemical potential is in the middle of a band. It's a band which is very flat. It has a very high density of states. There's tons of states for electrons to conduct. This should be a super highway for electrons and conduct super well. Yet, the conductivity is 0, okay? It's something that should not happen in single particle physics, but happens in many body physics. The interactions between the electrons lead to an insulating state when this should be a very good metallic conducting state. And the same thing happens if you put 2 electrons per more unit cell. We have correlated insulator states. Yeah? So that was the first sort of surprising thing that we found out in 2018. And the next interesting thing that happened is that, by the way, this behavior, okay, only happens if the twist angle between the 2 graphene sheets is very close to 1.1 degrees. More or less 1.1 plus minus 0.1 degree. Okay? 0.9, 1.3 doesn't work. Okay? So it's very specific to the presence of those flat bands, to that magic angle condition. And then what was even a bigger surprise, and that we found, is that if you now add a few electrons or a few holes to the correlated insulator state, okay, your system turns into a superconductor, okay? An electrically tunable superconductor, in fact. At certain density, you have correlated insulator states. You add more electrons, you have superconductivity. You are, in this case, more holes, you have superconductivity. You add electrons, you have superconductivity. Okay? So magic angle twisted Vallejo graphene is an electrically tunable superconductor. A superconductor you can switch on and off. Okay? When my students showed me this data, it reminded me immediately of the hundreds of times that I had seen these type of phase diagrams at seminars. This is the phase diagram of the high temperature couplet superconductors. Okay? Let me switch the axis so that it's in the same direction as this axis. Okay, now it's good. In high temperature couplet superconductors, at 0 dopings means actually 1 electron per unit cell. You have a mode insulator, a correlated insulator which is a mode insulator. You add holes and you have a superconducting dome. You add electrons and you have a superconducting dome. Okay. For magic angle twisted Vallejo graphene, add 2 holes or 2 electrons per more unit cell. You have a correlated insulator. You add holes, you get a superconductor. You add electrons, you get a superconductor. Yeah? Now, there are many similarities and also many differences between these two material systems and these phase diagrams. But one important difference is the fact that this is a theoretical phase diagram. In order to populate this with experimental data points, we have to grow hundreds of materials, often of different material classes, because not all materials can be grown in the same chemical composition and doping, etc., and do hundreds of experiments cooling down and filling this phase diagram with data points. Here, this is all done in a single device, in a single cool down, with a single chemical composition and single disorder realization. And I can go from here to here in 10 seconds dialing a voltage knob, okay? Whereas here I have to do hundreds of cool downs and spend years to populate that phase diagram. So that's something that obviously is advantageous and has attracted a lot of attention. Okay, let me tell you a little bit about the rise of Moret quantum matter. So we posted this in March of 2018. Okay, we announced it at the March meeting of the American Physical Society. And then the theory tsunami came, which is, within a few weeks, of us posting our results, there were all these theory papers, trying to understand what are the correlated insulators and superconductive properties of this. This list has now several thousand papers, actually, okay? Now, all kinds of proposals, were proposed, all kinds of things were proposed, for the order parameter, involving all letters of the alphabet. It could be S, P, D, S plus P, D plus ID, D plus F, all possible combination of letters of the alphabet were proposed. I have to say that, for me, coming from, before I did these things, I was just vanilla graphene, kind of researcher. And in that field of 2D materials, I always tell people that the angular cone of disagreement between theorists is about 20 degrees, a little bit here, a little bit here. In this field, is 360 degrees, In fact, it's 4 pi, it's in all directions, of space. So this was quite new to me, I was very disoriented, with all these proposals, When the first paper appeared, great, we have it. And then a completely different paper, then different, I'm like totally lost, But I have to say that we do not have yet an answer to all of these questions, but experiments are constraining quite dramatically now the possible options. Okay? It's no longer that everything can go, okay? We're slowly constraining. Now, maybe more important than these theory developments, which they're still trying to settle the question, are the experimental developments that happened since we officially published the paper in April 2018. Okay? The first thing that happened is that we have reproduced our own results in my group many, many times. Believe it or not, that doesn't always happen. So it's good when you can reproduce yourself. Okay, you start to gain confidence that this thing is real. Much better than you reproducing yourself is when other groups completely independently of you reproduce your results. Only then it becomes real science. Yeah? It's crucial. Other people have to be able to reproduce your results independently of you. Only then the community believes this is real science. Okay? And luckily for us, our results have been completely independently reproduced by dozens and dozens of groups, many groups, many papers. In fact, there's a big community now working on all of this. The other thing that we have done is that, after that initial observation of correlated insulator states and superconductivity, as I mentioned in the introduction, we have been able to realize plenty of other phenomenology and quantum phases of matter, and characteristics of quantum materials which have been observed in other correlated materials. For example, strange metal behavior, nematicity, Fermi surface reconstructions and cascades of phase transitions, pseudo-gap physics, etc. So we are exploring, this is clearly a family of correlated materials, and we're exploring, various different, aspects and facets of all of this. We have also discovered it's not just magic angle twisted by Liang graphene. Actually, using this trick of twisting things and creating more heterostructures, there are plenty of other Moiré systems that are strongly correlated and have interesting topological properties. For example, ABC trilayer graphene aligned to HBN, magic angle twisted bilayer graphene, 2 layers of graphene on top of 2 layers of graphene twisted. We call that twisted by. Moiré transition metal dichalcogenides. There are plenty of correlated systems. We have now several dozen correlated systems which are being investigated. Something which was quite crucial was the observation of ferromagnetism, the anomalous Hall, and the integer and fractional quantum anomalous Hall effect in these systems, because that brought the role of topology front and center to this problem. In fact, one of the nicest things that I've experienced over these past years is that this Moiré quantum matter has meant the merging of several condensed matter physics communities which were not talking that much to each other before. On one hand, there was this 2D materials and van der Waals, 2D van der Waals materials and heterostructures community, people like me, that did graphene and other systems. Then you have the people that did strongly correlated materials like high temperature cuprate superconductors, heavy fermions, iron pnictides. And then the people that do topological condensed matter physics, integer and fractional quantum Hall effect, topological insulators, Waals semi-metals, all of these come together in Moiré quantum matter. So you have all of these people talking to each other, and I get to participate in many discussions where I really didn't interact much with those communities before. So the fact that topology would play an important role, there were early theoretical works about magic angle twisted by Liang graphene, and then my collaborator Senthil at MIT, we published a paper. We already suggested that there would be all these nearly flat Chern bands in Moiré superlattices, different types with different Chern numbers, etc. And just about 6 months later, the group of David Goldhaber-Gordon at Stanford measured a very large anomalous Hall effect. So a Hall effect, finite RXY Hall effect at zero magnetic field in magic angle twisted by Liang graphene aligned to HBN. It's sort of a double Moiré heterostructure. And then 6 months later, the group of Andrea Yang at the University of California, Santa Barbara, they published the first quantized anomalous Hall effect in magic angle twisted by Liang graphene aligned to HBN. So the quantum Hall effect at zero magnetic field realized. Okay? The following year, two different groups, not the following year, this past year, 2023, several different groups have published something which is even more amazing, which is the fractional quantum Hall effect at zero magnetic field. That's known as the fractional quantum anomalous Hall effect. The first group was the group of Xiaodong Xu, and then also several other groups, worked closely after, where they realized this not in a graphene-based system, but in a transition metal dichalcogenide system, twisted bilayer molybdenum ditelluride. Here you can see a fractional member, 3/2 in resistance, which means 2/3 in conductance, happening at zero magnetic field. Yeah? And a little bit later, my colleague Lonju at MIT realized the fractional quantum anomalous Hall effect in complex systems called pentalayer rhombohedral graphene aligned to HBN. It's an interesting Moiré heterostructure between hexagonal boron nitride and a 5-layer graphene of a special stacking. Yeah? This is really quite spectacular and has created a lot of further interest because this phase of matter did not exist before. Okay? It was theoretically proposed, but had never been discovered, and it was discovered in these Moiré systems. There have been also a lot of other work on fractional Chern insulators, which is a state of matter which is closely related to fractional quantum anomalous Hall effect. Okay, and there were also in graphene-based systems and other systems too. Now, these systems, I've been showing you so far transport. You apply voltage and you measure resistance, and you measure something, or you measure zero resistance, superconductivity, etc. But everybody was very curious, like, oh, do these things really look like this Moiré, like those soccer balls and so on? So indeed, actually, these systems are perfect for local probe studies. So very soon after our discovery, people started to look at them with local probes, especially with scanning tunneling microscopy. A lot of the activity has been with that, but also scanning nanoscreen, scanning single electron transistor, scanning near field optical microscopy, scanning transmission electron microscopy, et cetera, et cetera, et cetera. Every near field technique has been applied to this system, okay? And in particular, even a new technique called the quantum twisting microscope has been invented. Now, instead of we just slapping these two the materials at a given angle, which is fixed. We choose any angle that we want, but once you make the device, it's fixed. You put contacts and it's fixed. Now people have invented a method where you can put one on top of each other and then do electrically, and you can vary the angle in situ. And you can study the properties of this thing as you vary the angle in situ. That thing is called the quantum twisting microscope. Very interesting development, okay? Not only that, I've been talking like if we are always dealing with 2 layers, but why stop at 2? We can put 3 on top of each other. We can put 4 on top of each other. We can put 5 layers. Turns out the magic angles are different. For 3 layers is 1.6 degrees. For 4 layers is close to 1.70 something. For 5 layers is 1.84. Okay, and the thing keeps going. Okay, so we call this the next generation Moire quantum matter, Moire magic 3.0, 4.0, 5.0, depending on how many layers you have. Okay? And many groups, including groups here at Harvard, my group at MIT, and plenty others have been exploring this thing. In particular, in 2021, the group of Philip Kim, who was my postdoc advisor, is professor here at Harvard, and my own group, we reported back-to-back papers in Nature and Science with the discovery of magic angle twisted tri-layer graphene, which turns out to be an even better and stronger superconductor and more tunable than the bilayer. The following, 2 years later, or not, the following year, 3 groups, the group of Emmanuel Tutuk at UD Austin, my own group, and the group of Stefan Nachpertz at Caltech, we showed that, magic angle tetra and pentalayer graphene are also robust superconductors. So now we have a family, If you have 2 layers, 3 layers, 4 layers, 5 layers, this is now enough people that we can call it a family, So enough members. Now, let me tell you, and the last couple of minutes I've been talking about electronics mostly so far, But it turns out all of these concepts extend beyond electronics. And let me show you a couple of examples of how this extends beyond electronics, also how this extends beyond graphene and transition metallic chalcogenides. So, we've been realizing all of these phases of matter with pretty much just carbon. In some cases, also maybe with HBN or with the transition metallic chalcogenide. You can realize most of them just with pure carbon. So it is the fact that you can play with this angle and the density of electrons. The playing with the density of electrons in these superatoms, this Moire structure, is the equivalent of going through the periodic table like this, and that's where we can realize, part of the physics is that. But we have hundreds of 2-dimensional materials, okay? Many of which, in their elemental, single layer form, can be quite exotic. So as you can imagine, now people are slapping on top of each other and twisting every possible combination of 2D materials. You have hundreds of people doing this angle, this other one, trying to see what can we discover, okay? Some of the things that have been theoretically predicted are a high temperature topological superconductivity when you twist double layer copper oxides. High temperature superconductors, they are layer materials. You can twist them and you can change the type of superconductivity you get. If you have 2-dimensional magnets, you can also twist them on top of each other and you can create something known as Moire magnets with Moire skyrmions and Moire physics in their magnetic properties. But that's also kind of electronics. Let me tell you about, Moire magic beyond twist electronics, okay? One of the first things that happened was that the cold atoms community said, hey, I can also twist my cold atom lattices. Why don't we do it, okay? So first, theory papers by one of the leaders of the field, Ignacio Cirac, and then experimentally, groups in China have already realized twisted cold atom lattices, and they're starting to explore the physics of twistronics, but with cold atom lattices. Okay? You can also do this thing not with electrons, but with phonons. Okay? So there is this thing called Moiré and twisted phononics, because this trick, this single particle trick that reduces the velocity of the electrons, that makes the flat bands for the electrons, can also reduce the speed of phonons and make flat bands for phonons. So you have this thing known as flat bands in magic angle vibrating plates, magic angle bilayer phononic graphene, acoustic twisted bilayer graphene, okay? You can slow down phonons, which have implications for sound propagation, for heat propagation, etc. You can also do this thing with photons, okay? Moiré and twisted photonics. Turns out, using a similar trick, you can slow down the speed of light tremendously, okay? And if your speed of light is very low, very small, then you can have all kinds of nonlinear devices, etc. This is actually, in fact, after the electronics, this is the fastest growing topic with many Department of Defense programs here, launched to study this thing, okay? And there are many, many interesting papers that have been published on twisted and Moiré photonics. Now, last slide. You can also, these regions that I showed you where the electrons like to be and not like to be, this creates local regions, regions where locally the density of states varies a lot. And the density of states is, an important component when you do chemical reactions, okay? So there is this thing called Moiré and twisted electrochemistry and catalysis, okay? So the group of Quaven and Bediako, for example, has been investigating locally with a little AFM pipette, how the electrochemistry changes in twisted bilayer graphene, in different regions of the Moiré pattern. Liang, who is the next speaker, together with Claudia Felser and Yang Zhang, they have studied Moiré metals, for catalysis, for hydrogen, evolution reaction, etc. It turns out to be better than platinum catalyst, at least theoretically. And last but not least, our high energy friends couldn't get behind. So there is this thing called Moiré gravity and cosmology, where people think that, you may be able to learn something about the universe, by looking, these are actually pretty serious people, by looking at, the strain patterns in twisted bilayer graphene, etc. Yeah? So with this, I want to end, this is of course not work that I do, it's work of a big team of people with lots of collaborators, great students, people like you, that come and do really fascinating work. And of course, always grateful to our supporters. And I want to thank you all for your attention and take any questions.
Behind, but we'll get a few questions. I don't want to make you but so late for lunch after Professor Fu's talk a little bit later.
So very quick question. Thanks for a fun talk of twistronics and twistology. I was wondering, you mentioned all the letters of the alphabet for the Moiré superconductivity. Do you think that there are triplets living out there?
Triplets, okay. So the superconductivity in magic angle graphene, we have now evidence that it may not be singlet, yeah? If it's not singlet, it means spin singlets. Does it mean it has to be triplets? Not necessarily. It can be a superposition or linear combination of singlets and triplets, yeah? But we have pretty good evidence now that it's not just standard singlets, yeah? But we don't know yet if it's triplet or it seems more likely that it will be a superposition of singlets and triplets, actually.
Hello again, I'm James. I'm a fifth year at Yale. I was wondering, of any of the subfields that got birthed from what you ended up doing research on, are there any you didn't mention that you were really excited about the directions they're going in?
I think, do you mean this last one, electronics or non-electronics related?
Are there any that you didn't mention in this presentation?
Did I miss anyone? Of course, you always miss someone and someone will complain and send me an email, Pablo, could you forget me? I think that's a pretty good survey. I mean, there are plenty of things that people are doing that I haven't mentioned, okay? Like, I did mention briefly ferroelectrics. That's actually a huge field now, Moiré ferroelectrics. I haven't discussed. If I had 15 more minutes, I would have included our work on ferroelectrics, but that's something that, we're doing and plenty of other people are doing. There is also a lot of work on Moiré optics, creating excitons in your Moiré pattern. They call them Moiré excitons, which are different from regular excitons in semiconductors. Huge field also, many people doing very interesting work. People are trying to make, all kinds of quantum sensors and even superconducting qubits with these systems because they can be interesting superconductors and interesting superconducting single photon detectors based on, these Moire superconductors. There are all kinds of things that are going on that I haven't mentioned, but I think the broad themes, I have more or less covered, or I try to do my best to cover them.
So I'm going to add the last question. One of the things that I find kind of most amazing about your work, Pablo, is that when I look at it, it looks like you may have found in Moire materials the Rosetta Stone for how you do high temperature superconductivity.
Oh, that's a highly controversial thing, You have the people that think, that's it, let's just understand this thing and we'll understand all correlated superconductivity in the universe. And you have the people that think, what are you talking about? This thing has nothing to do with cuprates. Sure, it might be interesting, but the explanation, come on, don't take away from us our cuprates and our explanations. So it's hard to tell. We don't know yet, okay? There are definitely many similarities between cuprates, or actually any correlated superconductor and superconductivity in Moire materials. For example, you can compare the absolute values of the critical temperatures. Those are important for applications, but from the physics point of view, that's not the most important thing. Typically, what's most important is how high is your critical temperature compared to how high is your Fermi temperature, how much density of electrons you have in your system, okay? And conventional superconductors that we understand have a very low ratio, okay? Aluminum, for example, has a TC of 1 Kelvin, a Fermi temperature of over 100,000 Kelvin, has a gigantic density of electrons, superconducts a little bit. All the unconventional superconductors, the cuprates, the pnictides, the organics, and magic angle twisted Vallejo graphene, and all the magic angle graphene-based systems have an extremely high ratio of TC over TF. Okay? In fact, for magic angle twisted trilayer graphene, is the highest of any superconductor in the world. Okay? And people think that that is an important ingredient to understand all those unconventional systems. How come that they have extremely high critical temperatures compared to the few electrons that they have, the very small density of electrons that they have? Okay? This system, 10 nanometers unit cell, we put 1 electron per unit cell, it gets nothing in terms of electron density compared to aluminum. The TC is higher than aluminum. Yeah? So that is something that I think gives people food for thought. Yeah.
So let's thank Professor Jarillo-Herrero again for a phenomenal talk. It's going to be a very, very short introduction of Professor Liang from MIT, who was a former Breakthrough Prize winner in physics.
New Horizons Prize.
But I'm delighted to have you here because the reason why I wanted you here is, for the life of me, I can't figure out topological quantum computing. And so I'm hoping today that you offer us some insight.
All right,
Thank you.
Okay. All right, thank you. It's a really great pleasure to be here. So today I'm going to talk about some recent work, both recent and not so recent, on non-reciprocal quantum materials. Okay, it's continuation in the theme of quantum materials, but I'm going to describe a new class of quantum materials that are emerging, and they show interesting non-reciprocal electrical optical properties. So as we know that quantum materials can exhibit a wide range of collective phenomena that you wouldn't expect from the just simple behavior of individual electrons. And for example, magnets, right? The magnets, electrons spin spontaneously ordered, breaking the time reversal symmetry, breaking rotational symmetry. In the superconductor, electrons pair up despite of the repulsive Coulomb interaction between them, and the electron pairs, they condense into a collective state that supports electrical current without any resistance. And over the last 2 decades, the new kinds of topological materials have been found. These include topological insulators. The material is insulating in the bulk with an energy gap. However, there exists conducting electrons on the surface. These surface electrons carry electric current and also carry spin polarization. And this might be useful for spintronics. And then we heard from the last talk that you take a 2-dimensional atomic thin materials and you stack them together by designing the twist angle, and one can create all sorts of magic, including magnetic properties, superconducting properties, as well as topological properties. So, so this talk, I'm going to focus on perhaps the simplest type of properties of materials that is manifest in their current voltage relation. Okay, and as we all know, that most of the materials, the IV curve satisfy the Ohm law. It's a linear relation, and the ratio is a resistance. And when you take out the volume factor, the resistivity is an intrinsic property of materials. And believe it or not, the resistivity of different materials at room temperature really span an enormous order of magnitude. Okay, this including really good conductors such as copper and aluminum, and there are highly insulating materials such as a diamond. Okay, and if we go to low temperature, the physics is even richer. We can get zero resistance states. That's a superconductor. Okay, but in all of these cases, the resistivity is a property of the linear IV relation. And a linear IV relation is called reciprocal because if we reverse the input current, and the current changes to minus itself, the voltage also get reversed. Okay, that's a property called reciprocal. But I want to ask a question, can quantum materials exhibit intrinsically non-ohmic IV relation? And in particular, I want to think about a nonlinear current voltage relation that breaks reciprocity, meaning that when we reverse the input voltage, the current does not go back to minus self. Okay, this also means that if you look at the resistance at a given input current, it takes a different value when they reverse the direction of the current. We get a current direction dependent resistivity. So is that possible? Now, this kind of a non-reciprocal current voltage relation has been observed in many electric devices, right? As we all know, for example, the semiconductor PN junction. And in this case, the two pieces of material themselves are unsurprising, very common. You can take a P-type of semiconductor right next to an N-type semiconductor, and then right at the junction, because of the electrostatics, because of the work function difference between the two materials, it creates a space charge layer, the depletion layer. You get a positive charge piled up on one side of the junction and negative charge on the other side. And then in this junction region, there's a built-in electric field. This electric field sets a preferred direction. So when you pass current, okay, in the forward, so-called forward direction, then the current itself changes the depletion length, and that changes the resistance of junction. And if you reverse the direction of the current, the effect is opposite. So for that reason, the current voltage relation is not linear, and it's asymmetric. So this is a classic example of a non-reciprocal, nonlinear IV characteristic. And the semiconductor PN junctions is the foundation of modern electronics. It underlies devices such as diodes, transistors, and used in solar cells, and etc. Now, one of the limitations from the fundamental physics point of view, one of the limitations of the junctions is that the junction capacitance sets a fundamental limit on the operating frequency. So that's why it's hard to operate semiconductor junctions up to very high frequencies such as terahertz. Also, if you look at this IV characteristic, at a very small input current voltage, in that regime, the device always behaves in a linear way. So it's always reciprocal for small input voltage, and you need really a threshold voltage to make this strongly nonlinear, right? So this threshold voltage is about 0.7 electron volt for silicon. Okay, so if we are interested in low power electronic devices, then there will be a bottleneck. So that's why perhaps if we can find quantum materials with a giant non-reciprocal electrical properties, maybe this opens up new possibilities for new technologies, especially in the high frequency, for example, terahertz frequency range, and in the low power assumption regime. So that's an interesting question from the potential application point of view. Now, so sort of what guided me into this research is really thinking about the basic symmetry in physics of materials. And for example, if we think about a non-central symmetric crystal, an example is shown here. Suppose, in the simplest example here, suppose I have a diatomic crystal, right, with different ions arranged in a quasi one-dimensional manner. Then, of course, this material is apolar. It has a well-defined polar axis. And then if you look at the IV characteristics going beyond the linear regime, then based on symmetry, there should be an additional effect that's allowed, that there could be a quadratic term to the IV relation, meaning that the resistance in principle can depend on the direction of the current. It depends linear on the current. So when we change the current direction, the magnitude of the resistance will change. Right? So this will be the kind of the non-reciprocal effect that I'm talking about. So from this symmetry point of view, then it seems that non-reciprocal effect should be quite generic in non-central symmetric materials. So is it really true that if we take the philosophy by Feynman, that anything can happen that will happen? Right? It's also known as Murphy's law. So the question is this valid when it comes to non-reciprocal physics? Okay. And before I tell you the answer, let me also mention that if I have an intrinsic non-reciprocity of a homogeneous quantum material without invoking any junctions, then this IV relation can in principle work at a very high frequency that's only limited by the basically scattering rate of the material itself, which is typically on the order of tens of terahertz. It's in the infrared frequency range. So that's why if we make the input signal to have a time dependence, then we can generate high harmonics. We can get second harmonics. We can get also DC components. That's called the rectifier. And one can also send in signals with different frequencies. Then the output will consist of sum and difference of these frequencies. So this could have interesting applications in high-frequency electronics, rectifiers, photodetectors, and I'll say more about this, something we explored a few years ago. Okay, so now, so the question is then why this non-reciprocal IV relation is so rarely observed? Now, one thing to notice is that actually nonlinear IV curve itself has been observed a long time ago. This is from the Bell Lab days, early days of semiconductor research. And as you increase the input voltage, the IV curve deviates from linear. But still, in this material, which I think is germanium, the IV curve is reciprocal. If you reverse the direction of the voltage, the current just gets reversed. Okay, there's no second order nonlinearity. And the absence of the second order nonlinearity in most of the conventional materials actually has a deep reason. That's because in addition to inversion symmetry, time reversal symmetry also relates states with opposite momentum. So on the time reversal, electrons' momentum get reversed and the current gets reversed. So if we look at the energy momentum relation for electrons in solids and take the example of conventional materials such as silicon or gallium arsenide or in graphene, as Pablo said earlier, this relation is always holds that the energy momentum relation is an even function. Ek is equal to E of minus k. And the transport theory of solids traditionally is based on the energy momentum relation. And therefore, under the condition of time reversal symmetry, meaning that in non-magnetic materials, even if inversion symmetry is broken, as it is the case in gallium arsenide, the symmetric energy momentum dispersion leads to the absence of non-reciprocal effects in the conventional transport theory. Okay. So really, to go beyond this standard theory, one has to think about various ways to either break the time reversal symmetry or to go beyond the conventional transport theory. And that's what I'm going to describe. So the first approach is to break time reversal symmetry with, for example, applying a magnetic field. And this has been thought about before, and even there are experiments. And for example, in the presence of a magnetic field, then a non-reciprocal IV curve is in principle possible. And in fact, it has been observed in several materials. And for example, you take a topological interesting film, and it has a surface states that's shown here in the dashed line. When you apply a magnetic field, because of electrons' momentum and spin is locked, the Zeeman energy from the magnetic field would distort the Fermi surface so that Ek and E minus k are different. The energy momentum relation is no longer symmetric. And then experimentally, this non-reciprocal component in the IV curve has been experimentally observed. A second order correction to the IV curve has been observed. However, this non-reciprocal effect is extremely small. Okay, if you look at the difference of the resistance under opposite currents divided by the average resistance, then this quantity, a dimensionless quantity, is less than 1 part per thousand. Okay, extremely tiny effect. And this is kind of expected because the time resource symmetry breaking comes from the magnetic field. The Zeeman energy is a small energy compared to the kinetic energy of electrons, the Fermi energy, okay, inside the material. So it's a small effect. So the question we are asking is, can we find the mechanisms and the materials with a very large non-reciprocal effect from quantum physics, okay? And so far, I've described this first approach, which is so-called the magneto-chiral effect. It's an immersion breaking material in the presence of applied external field, and we look for the non-reciprocal effect in the longitudinal resistance, okay, when the current and voltage are measured in the same direction. But now, let me think outside the box. So what if we consider transverse resistance? Okay, meaning if we pass current along x direction, we measure the voltage along the y direction. And the nice thing about the transverse resistance is that it can be zero in the linear regime, or it can be positive or negative. It's not dictated to be positive by the law of thermodynamics. Okay, unlike the case of the longitudinal resistance, which has to be positive. Okay, so this means that when I increase the input current, the current-dependent transverse resistance can actually, in principle, even exceed 100%. Okay, and we will show that indeed happens. Okay. So before that, let me first say a few words about how transverse resistance arise in the linear regime, in the linear response regime, and this occurs by the name of so-called the Hall effect, and that always requires either external magnetic field or magnetism that break time rules of symmetry. And the classical Hall effect was applying a magnetic field, and in the z direction, pass current in the x direction, there will be voltage in the y direction, and this Hall conductance is linearly proportional to magnetic field, which is very, very small effect in conductance. However, in the 80s, it was found that if you increase the magnetic field and work with semiconductors, this Hall conductance can actually be quantized into some integer multiple of e squared of h. This is called the quantum Hall effect. Now, without external field, the material itself can spontaneously break time rule symmetry. These are magnetic materials, and they actually can also exhibit anomalous Hall effect, the zero field Hall effect. And in the conductors, this is again observed a long time ago, and about 12 years ago, this anomalous Hall effect was found to be actually quantized in magnetic doped topological insular films, and this is similar to the quantum Hall effect, but now without external field. So all these cases are the linear response Hall effect, and they all require time rules of breaking. And we started together with N.T. Soderman, who was a Pablo fellow at that time at MIT. We started to explore the possibility of a Hall effect in the nonlinear regime and preserving time rules of symmetry. So again, if we take a time rules invariant material, at the level of linear response, the Rxy has to be 0. However, if we go beyond the linear response regime, we found that a quadratic current voltage relation is allowed. And this means that if we pass a current in the x direction or apply a voltage in the x direction, we can get a transverse current in the y direction if the material has a polar axis, okay, along the polar axis direction. There could be a quadratic Hall current. And in this case, if we look at how the resistance behaves, the resistance actually changes sign when you flip the applied voltage, and this non-reciprocal coefficient will actually diverge. Okay, this is possible because I have 0 Rxy to begin with. Right? That's unlike in the case of longitudinal effect. I have to compete with the usual Ohm's law. Okay, here in the transverse direction to the linear order, because of time rules of symmetry, there's no Hall resistance. But then beyond the linear response, there can be a quadratic effect. So we call this nonlinear Hall effect. Now, how this is possible, despite the time rules of symmetry in the system, so this requires us to go beyond the conventional transport theory, and we talk about how quantum mechanics can affect the transport of electrons in solids. So here, in addition to thinking about the electrons' energy momentum dispersion, energy momentum relation, one has to also take into account of the nature of electron wave functions within each unit cell. And that's where quantum mechanics comes in. So in this simple example of a diatomic crystal, the electron wave packet in general has amplitudes on both types of atoms, and in fact, it's generally a coherent superposition between these two types of atoms. And the amplitude are generally momentum dependent. K is the center of mass momentum of the electron, block electron wave packet. So as when in the presence of external electric field, the center of mass momentum is accelerating. Okay, this is basically the quantum version of just Newton's law. However, as crystal momentum changes, the distribution of the electron wave packet within these two types of atoms are also changing. So you can imagine that as K accelerates, as K increases, more and more weight of the electron wave function in the unit cell are on the red atom. So this then creates an additional current, the so-called enormous current, right? So this is an unusual effect that the electric field actually generates a current instead of generating acceleration, okay? And the proportionality constant between the enormous velocity and the electric field is called a Barré curvature. And this Barré curvature is a quantum geometric quantity that describes the geometry of the block wave function in K space. And it gives rise to this enormous velocity because electron wave function is redistributing within the unit cell, within different parts of the unit cell. And interestingly, this enormous velocity is always perpendicular to the applied electric field. And this effect was first described in this classic work of Karplus-Latinger, but it's only in the 1990s that by work of Chen Yu and others that made a connection to this quantum geometry. So there's a simple way to visualize this effect. You can think of electron wave packet in a solid as has a self-rotation around its own center. So in addition to moving with a finite velocity and with center mass velocity and a finite with a well-defined position, the electron also is generally self-rotating around its own center of mass in materials that break inversion symmetry, in materials that break time-reversal symmetry. And the Barré curvature is, roughly speaking, related to the degree of self-rotation. So if you have a rotating object moving in the external field against the external force, then a rotating object gets deflected sideways. This is the so-called the Magnus effect, like a rotating ball, that get deflected sideways when moving under the friction of the air. So this Barré curvature effect, enormous velocity, is really just a quantum version of that. Okay. So now in the level of linear response theory, when we look at the total current, then we, in the transverse direction, then we sum the enormous velocity of all the electrons in the occupied states. And because enormous velocity is already linearly proportional to electric field, then to the first order in the external field, the Hall current is obtained by just using the equilibrium electron distribution. And this leads to the famous TKN formula for the Hall conductivity that is expressed entirely in terms of the Barré curvature of occupied electron states in equilibrium. And in the case of a completed field band, then we get an integral Barré curvature over the entire Brillouin zone, and that's mathematically guaranteed to be an integer, and that explains the quantization of the Hall conductance in without external magnetic field. Okay. On the other hand, I'm focusing on materials that are time-reversal symmetric. And in this case, the Barré curvature is still, can still be present, but it has to there has to be equal and opposite Barré curvature at opposite momentum. And at the same time, the electron's energy momentum relation is symmetric. This means that if we look at the Hall current at the linear response level, we are integrating over Barré curvature over all occupied states, symmetric in K. So the distribution function is symmetric in K, the Barré curvature is odd under K. So then this Hall conductivity vanishes. So for time-reversal symmetric materials, the Hall effect vanishes at linear order. On the other hand, I've always been interested in this inversion breaking materials, time-reversal symmetric, but inversion breaking materials. And in that case, Barré curvature can still be present. It can, in fact, can be very large. And some examples as known from before is transition metal diacrylamides. Another example is graphene on boron nitride substrate. And in all these cases, there are actually a strong Barré curvature at the Brillouin zone corner. But again, they take opposite signs at the two values, k and k prime. So the total barrier curvature vanishes, so there's no enormous Hall effect. But now let's look at the Hall effect go beyond the linear response. So we realized that if we go beyond linear response, let's think about a current carrying state driven by an external electric field. And in this case, there will be more right movers in the same direction as the electric field than left movers going against electric field. And in this case, there's a population imbalance between left and right movers. And suppose when the left and the right movers carry opposite barrier curvature, guaranteed by time rules of symmetry, then this population imbalance will then lead to a net barrier curvature. Okay? And this amount of barrier curvature is proportional to the applied electric field. And then this barrier curvature further drives an enormous current, which now is second order electric field. So because of this, we can, in the time rules symmetric systems, we can get a Hall current that starts at the second order due to this equal and opposite barrier curvature at opposite momentum. And in fact, one can find a very compact formula for this enormous Hall current at the quadratic order, and it all requires thinking about the spatial, the distribution of barrier curvature in momentum space, basically the derivative barrier curvature with respect to k integrated over all occupied states. And that describes the nonlinear Hall effect. And we call this quantity barrier curvature dipole. It requires both barrier curvature and it has an asymmetric distribution in the k space. And because barrier curvature is routinely calculated now in DFT calculations, so this formula allows us to actually explore the material database and to predict nonlinear Hall effect. Okay. And in our early work, we considered a topological crystalline insulator. Won't go into the details. These are materials which has a surface state which under structural distortion generates a Dirac mass. So we have a massive Dirac fermion that carries barrier curvature. And also, in these cases, the Dirac cone is tilted. So there's a preferred directionality. There's a barrier curvature dipole in this leading selenide, leading telluride materials. So that's our prediction from almost 10 years ago. And 3 years later, my experimental colleagues at MIT, working in Pablo and Niu's lab, led by Chong Ma and Su-Yang Xu, they came up with their own material. This is a bilayer WTE2. And in this material, the layer stacking breaks inversion symmetry and creates a preferred in-plane polar axis. And on the zero external magnetic field, when they measure the current voltage relation in the transverse geometry, and here shows that the transverse voltage is indeed quadratic in the longitudinal in the input current. Okay, so this is the first observation of the nonlinear Hall effect in any material, and also this response is found to be very large at a low temperature. Okay, and back to the this more recently. The material that we considered, this topological crystalline insulator material, there's an experiment from Japan that showed that if you take this leading telluride film and the experiments at room temperature shows that there is a large nonlinear Hall effect. Okay, and in fact, this effect can be trained by the electric pulse. So the electric pulse can switch the polar axis on these leading selenide materials, and when the polar axis switches, the nonlinear Hall effect changes sign. Okay, so this even led to the possibility of some barrier curvature dipole-based memory devices. Using a input electric pulse, one can switch the polar axis, and that can be used to record information. And by using the nonlinear Hall effect, one can measure these memories. Okay, so now another interesting direction is to go beyond these low frequency transport measurements, and because its effect is intrinsic, does not rely on any junctions, it should be able to survive even at a very high frequency, even in the terahertz regime. So we propose that if you take a nonlinear Hall material and it shine microwaves or terahertz radiations, then it develops a transverse voltage that can be measured. This is a way to for RF and terahertz sensing. And because this rectification effect, because of rectification effect, that high frequency radiation will be able to generate a DC voltage, DC current in the transverse direction. So this, in principle, does not require external power, and it can have very high sensitivity. And also, it works in a very broad frequency range. Because it's all electronic, its response can be very fast, and finally, can even work at the room temperature. So this is some could have interesting applications. And this is a recent experiment from China that showed that in this topological sand metals, cobalt ditelluride, and indeed the nonlinear Hall effect has been observed even in the terahertz frequency range. And using an antenna to enhance the terahertz electric field, and they find that a transverse DC current arises when the electric field is in the polarization is in the right direction, when it's in the Hall geometry. But this goes away if the electric field is in the other direction. Okay. So the other possible application is based on energy harvesting. So we know that if we can convert high frequency radiation, electromagnetic waves into a DC electric power, this would be useful. And for example, solar cell based on silicon PN junctions, these are widely used already, and they work for photon energies above the band gap, which is 1.5 eV. But then there's also a lot of electromagnetic energy at frequencies below this 1.5 eV, and these are wasted. So on the other hand, the nonlinear Hall effect I talked about actually works from DC all the way to the terahertz regime, and so this could fill in a gap in the solar energy harvesting. And one can actually think about the nonlinear Hall effect as closer in spirit to the microwave power transmission, and this was already demonstrated back in the 60s, 70s. If you combine the Schottky junction, Schottky diodes, and with an antenna, and they can be used to rectify microwave radiation. And here, the challenge is that it generally works on the very large microwave powers because of the threshold voltage for PN semiconductor junctions. But imagine we replace these junctions with intrinsic nonlinear Hall materials. Because of the IV curve starts directly from the quadratic order, right? This is like nonlinearity in extreme form. So this could be useful for microwave energy harvesting. So recently with my student, Yugo Onishi, we actually did a simple calculation, estimated the power transmission efficiency, and that generally depends on the matching between the internal resistance of the material and the external load. But under the optimum condition, the power transmission, power conversion efficiency can reach something like 40%. Okay. So, and in the last few minutes, let me switch to yet another kind of a non-reciprocal effect, not in conductors, but now in superconductors. So this was a reported experiment that's reported this effect in 2020 from Japan, and in artificial superlattice of superconductors of these niobium, tantalum, and vanadium. This sort of a tri-layer sandwich structure breaks inversion symmetry, and then under external applied magnetic field, it was found that the critical current is different in the opposite directions. Okay, and as a result, for a certain amount of input critical current, 6.6 milliamp, and the system is resistive in one direction, but it's superconducting in the other direction. So in this sense, it's a very large non-reciprocal effect. Resistance goes from 0 to non-zero, depending on the direction of current. So this created a lot of interest, and many theorists, including us, started to study the superconducting, so-called superconducting diode effect. And this, unlike the case of conductors, it is generally believed that superconducting diode effect requires breaking both inversion and the time reversal symmetry, because the superconducting state is a dissipationless state. Okay, and I won't go into the mechanisms for the diode effect. There are many, and one example, just briefly sketched here, is that for a conventional superconductor, both time reversal and inversion are present, so there's no such diode effect. But if you have a finite momentum superconductor in which the Cooper pair carries finite momentum even in the equilibrium ground state, and in this case, then the critical current along and against the Cooper pair momentum direction turn out to be different. In other words, the Cooper pair momentum in equilibrium sets a preferred direction. That is the analog of the electric field in the p-n junction. Okay, so one of the challenges in understanding the superconducting diode effect is that it requires to measure the asymmetry of the critical current. One has to apply a large current to really destroy the superconducting state, to drive the system from superconductor into a normal metal. And in the case of the large applied current, there could be problems with Joule heating, could be problems with vortex dynamics. So that makes it challenging to disentangle intrinsic superconducting diode effect from more mundane mechanisms. So that's why recently we started to think about a better way to probe non-reciprocal superconductivity. This is work with my student, Margarita Davidova, and the new postdoc, Max Gear. And the idea is that instead of thinking about the property of a superconductor under a large applied current, we think about its property in equilibrium. Okay? So one of the most fundamental properties of superconductor is the energy, quasi-particle energy spectrum. Quasi-particle energy spectrum. And we all know that when pairing occurs, the states near the Fermi level acquires an energy gap. Right? So this, what is shown here is a quasi-particle energy spectrum as a function of momentum. Okay? Now, usually this gap is symmetric, k to minus k, and this is for conventional superconductors. However, for a finite momentum superconductor, or for whatever reason, suppose the system breaks time reversal and inversion symmetry, then in general we expect the quasi-particle gap spectrum to be k minus k asymmetric. And therefore, the energy gap at k minus k is also different. And this then will show up in a very clean way if we consider a normal superconductor junction, okay, NS junction. And electrons, consider electrons instant into the superconductor from the normal region. And then depending on the instant momentum, if the momentum of the electron is parallel, is towards the interface, then the instant electron will be sensitive to the gap on one side of the Fermi surface. On the other hand, if I have a hole going in the opposite direction, which also corresponds to current flowing into the superconductor, then the holes will actually be probing the other part of the gap on the opposite side of the Fermi surface. And when the symmetry is broken in the superconductor, the gap is asymmetric, and this will lead to an asymmetry in the IV characteristic. So the better way to plot this is to look at the differential conductance as a function of the applied voltage in the NS junction. So here I'm showing the case when the junction is transparent. And for conventional superconductors, the famous BTK formula tells us that the conductance inside the superconducting gap will be enhanced, reaching twice the normal conductance. However, for non-reciprocal superconductor, and one way to achieve this is to think about superconductor with finite momentum, and you can see that this doubled in conductance now occurs at a finite. It centers around the region at a finite bias voltage. So in this case, the IV curve is clearly asymmetric. So in other words, this NS junction can be a good way to probe the non-reciprocal, intrinsic non-reciprocal properties of the superconductor. Okay, so let me just summarize that the non-reciprocal quantum materials, both in conductors, in superconductors, there's a lot of interesting physics. On the one hand, it's related to the basics of quantum mechanics in solids, including the barrier curvature dipole. These effects can often be very large in topological materials because of the large barrier curvature there. And they manifest as nonlinear Hall effect, as superconducting diode effect. I didn't have time to go into it, but also in ferroelectric materials and in antiferromagnetic that breaks symmetry. The non-reciprocal effect has already been observed. And there's now currently a lot of interest in pushing for these effects towards high frequencies, including microwave and terahertz, and they might offer interesting applications in energy. So let me finish by thanking all my collaborators. So the work on nonlinear Hall effect started in collaboration with Inti Soderman, now in Germany, and the work on applications of the nonlinear Hall effect both for RF and terahertz sensing and for energy harvesting. It's done in collaboration with Hiroki Isobe, Yang Zhang, and my current student Yuko Onishi. And the work on superconducting diode effect and the non-reciprocal superconductivity is done in collaboration with former postdoc Noah Yuan and my current student Margarita. So with that, thank you for attention.
Okay, thank you. That was a very good presentation. The question that I have is regarding the antenna that you showed earlier. Why would you want to put a passive device that actually bring in nonlinearity, distortion? Why would you want to bring that into the RF chain of the system?
So the role of the antenna is to really just enhance the electric field in the active region. So because the nonlinear effect is quadratic in the applied electric field, so you need a large applied electric field to get a big effect. So the role of the antenna is basically to concentrate the terahertz field in this microwave or terahertz field in this active region.
Okay, that's not the. I was referring to the previous one, to the previous slide that had actually the circuit.
The circuit, which so the the experiments here, for example, right, are not in the microwave regime. These are actually very low frequency. These are transport experiments. Experiments.
Okay.
And the message here is that the same physics for the transport also applies to the microwave and terahertz regime, because all these are based on intraband barrier curvature dipole effect. Okay, so that's a key thing I want to emphasize. Yeah.
Let's see. I had a quick question.
Yeah.
So in the polar metal system, over here.
Okay. Yeah.
Yeah. So if you have a polar metal, right,
Yeah.
like calcium 327, right?
Yeah.
Would you expect this because you've broken time reversal symmetry, you've broken
Absolutely.
inversion symmetry? So like what would you expect there?
Yeah.
Because that seems like an easy case.
Yeah. In general, polar materials should have a nonlinear Hall effect. Yeah. Absolutely. So the question is really about the magnitude. Is it large or is it small? Yeah. I don't know about the oxide. So far, all the experiments I'm showing you are basically semiconductors or 2D materials, transition metal dichalcidides, and I'm not aware at this point the experiments on oxides. So it's interesting. Yeah, it's a very interesting question. Indeed, there are many polar distortions in oxides. Yes. Yeah. So I think one interesting class of materials might be oxides with smaller gaps. Because if you have a large gap, right, large band gap, then the barrier curvature is usually small. Barrier curvature usually comes from mixing between different bands. Right? If you're near a band crossing, anti-crossing, that's when the barrier curvature is large. So it might be that in these oxides, the barrier curvature is small. But again, to my knowledge, nobody has to actually measure that. Yeah, so it's an interesting question. Yeah.
Stop there, so I won't steal but so much of your lunch, because I want you to come back here on time for the start of the next session. As I mentioned, I think they're going to group everybody together so that we can take a picture out in front, and then lunch will be upstairs in Jefferson 450 as before.